All right, guys. Morning. Thanks for showing up. I'm preaching to the choir here, but I know spring break's up right around the corner. Yeah, this is definitely like the lull of the semester. Right? Maybe. Okay, maybe for some people. I just know like this semester, this time of year is really easy to like kind of get sidetracked and be like, okay, we're just gonna kind of cruise over into other stuff. And I know I'm talking to you guys who are actually here, but everybody here in the computer, definitely try to keep going strong during this time. This stuff that we're covering today is going to be like more conceptual. There is a little bit that you're going to need for your homework. But this is a very like practical application of subsurface investigations. So I don't remember, does anyone work for geotech firms now? I think some people were here. Has anyone like worked with a geotech firm, like seen boring plans or anything? Okay, well, even if you haven't yet, you will in the future. So understanding like where this data is that the geotechnical engineer is magically giving you and basing their whole reports off of, knowing the limitations of the testing that come with that type of testing procedure is really important. So that's what we're going to be going over today, subsurface investigation, specifically SPTs, standard penetration test, and CPT, cone penetration test. So the overview of that stuff. So just some updates and stuff for the week. Lab 3, lab 4, you guys know about all the labs and stuff. Hopefully you got a chance to see that homework 2 was posted. That's going to be due next week. And on like the fun side of things, there's 2 events coming up. One is tonight, the ASCE trivia night at Green Room. I've already talked to a few of you guys, but if you're free tonight and you're in the Jacks Beach area, definitely suggest coming by. This is part of the E-Week, which is put on by all of Jacksonville engineering. So there's going to be engineers from all different disciplines. It also supports ASCE for their trip to Tallahassee coming up. But it's a great opportunity to network and to get to know other professional engineers in not like a suit and tie setting. A lot of that kind of just personalized communication is going to be super important to develop those skills like outside of a career fair or outside of, you know, a professional event. So it's going to be like a good opportunity at least to practice that. Also, the career fair is next, whatever March 1st is, Tuesday. If you guys have gone to those already, you know it's a really good event. There's like a bunch of employers over there on the other side of campus in the Herbert Center. So definitely stop by that if you get a chance to. I wanted to at least put that on your radar. All right, so we are pulling from a bunch of different textbooks. Yeah.
Are we going to do a quiz this week?
Yes. Yeah, there was a quiz this week. Yeah. So we're pulling from a bunch of different resources. The ASTM for SPTs, we'll pull from that. There's also this website where I'm getting all these videos from, geoengineer.org. It's kind of like a cheesy sounding website, but there's a lot of information on there that's open resource. So anything like that you may be seeing in this class that maybe like sparks your interest and you want to learn more about, you can go on that website. And then there's these like drop down tiles of all these different geotechnical engineering topics. And then all like the professors who are relevant in that specific area will post their content on there and stuff, and you can review that. Also, these 2 reports, you don't need to like worry about these yet, but when you start working, especially if you're working in a geotechnical engineering capacity, you will definitely use these 2 reports. One's by the Federal Highway Administration, and the other one is by this dude named like Robertson, who is like the godfather of CPTs, I guess you could say, cone penetration testing. He like just publishes and does a lot of research in that area. So he made this really helpful guide. So I'm taking a lot of figures from that too. So last class, we already talked about the importance of doing a subsurface investigation, right? Like we can use geology, we can use like the understanding of nearby locations, but when it comes down to it, we always need to perform some type of subsurface test at our project location to verify the soil conditions. And most of the time we're going to use some type of boring technique where we can physically get a soil sample And then we can bring it to the lab and have the geotechnical engineering interns and lab managers do all that type of work. So of course, there's a lot of limitations with just using a single boring. Because if you think about it, you're drilling a hole that's 2 inches in diameter, and then you are hoping that that is representative of the entire like 100-acre site or something, like a couple acres. So that if you actually look at it, like the percentage of the area that we're investigating is like usually less than 0.1% surface area wise. So there's already a lot of inherent error built into that because we, have a lot of uncertainty of not being able to test the entire location. So we need to ensure that the actual data collection is of high quality too. So the soil samples that we're collecting, the boring, the investigation techniques aren't including any additional errors just to stack on top of that. So these are some of the guidelines here, these spacing, but of course it's up to the geotechnical engineer or the client to really define how much testing is performed at a site. I've used the example last week, FDOT, if you're doing a bridge and these bridges have these piers, what they're called, or these columns that go from the bridge span down to the ground. Usually they'll require at least one boring per pier or one of these columns. But in some areas where the ground conditions are highly variable, like in the center estate where there's the issue for sinkholes and the vulnerability or the potential of sinkholes, then they may do additional testing in between those piers or laterally a couple borings as well. So it all depends on the project, what the project is used for, where it is, and how much the person is willing to pay for it. So of course, the majority of the subsurfacing is going to start with boring. And so I wanted to at least go over the boring process, the boring process. That isn't really that boring because there's a lot of steps if we think about it. We can all picture okay, we just drill down into the ground and we collect soil samples. But the actual steps that it takes to get a drill bit 100 feet underground without that hole collapsing in on itself adds a lot of additional things that we can often overlook. So I have this little video, I hope it ends up playing, but it kind of illustrates the boring process and the sampling process. So 2 things to look for real quick. One, they'll talk about the type of soil conditions and the ways that they mitigate the potential of the void or the hole collapsing in on itself, right? If we go to the beach and we start digging a hole, eventually we'll get to a depth where the sand is just collapsing in and we can't dig any further. So if you're doing a boring and you're trying to collect a sample 100 feet down, then that's obviously an issue. We need to mitigate that. We need to perform some or add something to that hole so it doesn't collapse in on itself. Another thing to think about is the actual drilling process and how long this takes, with 2 pieces of equipment. So we need the drill, the drill bit that's going down and removing the soil, but then we need to replace that drill bit with a sampling bit and collect a soil sample. So keep that in mind. I'll kind of skip through this. I don't know if the sound will actually work. Come on, bud.
Drilling is similar regardless of the type of drill rig used. First, we position the rig. Regardless of the type of drill rig used. First, we position the rig on the location where we wish to drill.
Golly, come on.
Whatever.
We'll just go through it kind of quick.
Location where we wish to drill. Then we erect the drilling boom or mast to make sure it's vertical. The drill head mounted on the boom is the mechanism used to perform the drilling and sampling operation. The drill head provides 2 motions to aid in drilling. A torque can be applied to rotate the bit, and a vertical thrust can be applied to raise and lower drill bits and other equipment. There are many different drilling and sampling techniques you can use to investigate the subsurface conditions. One of the simplest is the open hole method using solid stem continuous flight augers. The flights on a continuous flight auger run the full length of the auger. At the tip of the auger is a cutting bit. The inset photo shows 2 different diameter solid stem augers with 2 different types of cutting bits. The auger is rotated and pushed into the ground by the drill head. The bit at the tip of the auger loosens the soil at the bottom of the hole, and the flights carry the cuttings to the ground surface. An engineer or geologist can estimate when new soil layers are encountered by observing changes in the cuttings as they're brought to the surface. These cuttings can be collected as bulk samples. However, they are low quality samples because they're completely disturbed by the cutting process, because soil from the upper layers can contaminate soil from the lower layers as the cuttings are carried up the auger flights. When the boring reaches a depth where a higher quality sample is desired, the auger is removed from the hole to make room for the sampling equipment. In this method, the borehole must be able to stand open without support, which is why we call it the open hole method. When we wish to take a sample, we replace the auger bit with a sampling tool or sampler. Nearly all soil samplers consist of some sort of hollow tube, which is inserted into the soil to retrieve the sample. There are many different designs of samplers to suit different soil conditions, but the basic process of sampling is similar for most of these samplers. The sample tool is lowered to the bottom of the boring and then pushed into the soil below the bottom of the boring. When the sampler has reached its full depth, the rods are twisted to shear off the bottom of the sampler, and the sampler containing the soil sample is retrieved from the boring. The sample is then stored for later analysis and testing. The sampling tool
And then brought
is
to us.
replaced with the auger, and the auger lowered back down the hole. Augering continues until we reach a new layer where we wish to take another sample. The auger is then retracted from the hole and replaced by the sampling tool, and another sample is taken using the same process.
So in this example, it looks like it's like 5 feet down, right? It's not a big deal, but if this is 50 feet down, there's so much rod that needs to be pulled up before they can replace it with the
In these
sampler.
circumstances, we use a heavy wall sampler that can be driven into the soil using a drop hammer. The process is similar to retrieving a push type sampler, but uses different equipment and a different sampler. The open hole method only works if the soil is stiff enough and strong enough to remain open after the augers are removed.
So not in
While
Florida.
it is often possible to use the open hole method, many times the soil is not able to maintain an open. Is similar regardless of the type of
Golly.
is similar regardless of the type of drill rig used. First, we position the rig over the location where we would
Okay, let me see if I can do this real quick.
wish to drill. Then we erect the drilling boom.
Where are you?
It's similar regardless a sample is desired, another sample is taken using the same process.
Well, this sucks.
Because
Anyways.
there is or no cohesion, the soil at the sides of the hole may cave or fall into the boring. This is particularly a problem when drilling in sands below the water table. When squeezing or caving conditions occur, we must use a different drilling method that will support the borehole during the sampling process. One method that can be used in caving or squeezing soil conditions is the hollow stem auger method.
So what I want to skip to,
We use it instead of
this is the most common way of drilling in Florida, at least. Because Florida, the water table is so shallow, right? So we can only dig so deep and there's so much sand that like normally you get to a certain depth and it would just collapse in on itself. So in Florida, what we use is a driller's mud, which is bentonite, which is a type of clay mixed with water, and it forms a slurry. So kind of like similar to that material that we made during the lab this week. So this driller's mud is what they call it. Again, that's bentonite. It is more dense than water, and it actually fills the hole and allows and pushes up against to keep the hole sides open so it doesn't collapse in on itself. So as we are drilling in Florida, which they'll talk about here in a second, the driller's mud is circulated and pushed into the hole and then back out of the hole, and that removes all the cuttings as we are drilling into the ground. So the issue though with this is this driller's mud, if we hit a loose material, like a loose sand or something pretty deep, the pressure of this driller's mud can actually disturb the sample and it can move laterally. It can also mix with some of the fine grain samples. So when you pull up a soil sample and bring it to the lab, you have like a mixed in driller's mud with it as well. So this is kind of the issue that as a geotechnical engineer, you may come across this in some of your lab samples. You'll be like, what is this nasty gray stuff mixed in with my sample? Is it natural or is it this man-made added material that's driller's mud? So that's what they're referring to here. But it's just one of the limitations of having to drill below the water table.
This method uses a slurry or drilling mud to flush cuttings out of the hole. The drilling mud or slurry is a mixture of either bentonite and water or a polymer and water. The purpose of the bentonite or polymer is to increase the viscosity of the slurry, which makes it easier for the slurry to carry the cuttings from the surface. Special equipment is needed to handle the drilling mud, including a holding tank, a pump, and a swivel head. The pump circulates the drilling mud from the holding tank through the swivel head into the top of the drilling rod. It then goes down the hollow stem inside the rod toward the cutting bit. The boring is advanced using a drill bit at the bottom of the hole. The drill bit or cutting bit is turned by the drilling head and loosens the soil at the bottom of the hole. The drill bit contains ports that allow the drilling mud being pumped down the hollow stem to exit out the sides of the bit into the annular space outside the drill rod. The mud flows up this annular space and carries cuttings away from the bit and out the top of the hole. The cuttings settle out of the drilling mud in the holding tank, and the clean mud is recirculated back down the drill rod. Driving the drill bit of a rotary wash boring takes much less energy than driving a long continuous flight auger. Therefore, rotary wash borings can advance much more quickly and reach greater depths than auger borings. In addition to flushing cuttings from the boring, the drilling mud also provides a hydrostatic pressure along the sides of the drill hole. This can help to stabilize the hole and allow drilling in moderate caving conditions. When we reach our desired sampling depth, the drilling is stopped and all the cuttings are flushed out of the boring. The pump is then shut down and the hose disconnected from the swivel and the drill rod removed from the hole. Drilling equipment is replaced with sampling equipment and a sample is taken directly through the drilling mud. Another method that can be used to advance the boring in caving or squeezing conditions is the casing method. In this method, a large diameter pipe is driven into the ground below the depth of the boring. The hole is then cleaned out using either the auger method or the rotary wash method. The casing supports the side of the hole and samples can be taken in the undisturbed soil below the casing. So let's summarize. There are many types of drilling.
Okay. So the main thing that is important to understand for that is, especially in Florida, we use that driller's mud a lot. So if you remember the standard penetration test, which we talked about last week or last class, it consists of driving a sampler and counting the number of blows or the number of hits from a hammer it takes to drive that sampler a total of 18 inches, so 1.5 feet. And what we do is we count the number of blows it takes to penetrate 6 inches of that. So this little picture here shows that it's 0.15 meters, but we count a number that it takes to advance it 6 inches here, and then another 6 inches here, and then another 6 inches here. So what we end up doing though is the actual end value that we would write down on a report and like share with our client is the addition of the last 2 advances. So we advance it 3 times and we count it 3 times, but we only count the last 2 advances. And that's strictly because of the fact that there could be cuttings or there could be some type of driller's mud that is going through that first 6 inches of penetration. So the drilling process, we have this massive drill going into the ground and it's pressurizing water and it's disturbing the soil conditions at the end of that hole, right? So if we took a sample and a strength test of that first 6 inches, that first 6 inches is going to be really disturbed and it's going to be like messed up from the drilling process. So that's why we only add the last 2 counts. So the last two 12 inches. So last two 6 inches. So we only count that last 6 inches. So I mentioned last week too, like this is a very like basic test, but it's like it was developed in, I think like the 1902, I think I saw is when it was developed. And now obviously we have a better way nowadays with better equipment and understanding like the correlations between everything. But it's a very elementary test, and I have a video of it here just to illustrate this. If anybody ever gets a chance to see this in person, I highly recommend it. So I'll kind of just illustrate it at least. So what he's doing, they're augering right now. So that's the continuous flight auger. So that auger on the outside is pulling all the soil up, even though you can't really see. It's starting like to have a little mound on the base of it. So they're going down to their required depth. So now they're going to retrieve the inner diameter of the auger. So the auger is like a straw. So the inside is hollow. They're pulling out the drill bit. Now they're putting on the split spoon sampler. So that's the hollow like tip that is going to be collecting the soil sample. Again, this is like 5 feet, 6 feet down. So there's only like each rod comes in about like a 4-foot section. So if you're like 100 feet down, you're bringing a lot up and having to put a lot back down in it. So it takes a lot of time. This is the hammer moving over to the top of it. That hammer is 140 pounds. In true geotech fashion, to measure 6 inches, they just take a piece of chalk and an old ruler and they mark it on the actual drill rod itself. So what he's doing is marking 6 inches, 12 inches, and then 18 inches on the drill rod. And they just count. So what in that guy's head, he just counted to whatever number 3 times as it advanced each time. And then he'll like write it on a boring report. So that's where that end value actually comes from. And what you'll see, like if you start when you start working and you start working with geotechs, that end value is like the coveted, like most important number for a site. And this is how it's obtained, like just from somebody counting the number of hits. They'll do there. So he's removing the sampler. And yeah, over there, they bring it onto a thing to take the sample out. So what the results will actually look like is something like this. This is actually one of the reports I did from a long time ago, but I don't know if you can read any of that stuff, but if you can, it's okay because nobody else really can. So the drillers have their own way of like marking all these things, but then the goal is to take this and to turn it into something that we put in the report. So these end values right here, oops. These are those end values. These are the blows per foot. if you look at your slides, those are shown right here in this section. Other things that they say, this says gray sand, gray silty sand. So this is the description of the soil sample at each depth. And then the depth is shown here. So this is the second page. This is at a 51-foot depth. This was over like kind of south of Tallahassee. And then we'll have other information here where we have the drill rig type. So this is a CME 45, and we'll talk about the importance of the drill rig type in a second. And then other things like the outside diameter, the weight of the hammer, and the type of hammer used too. So by looking at that video, maybe because it's super early, you guys haven't thought this yet, but by looking at that video, you can probably see there's a lot of like variables involved. Like what would happen if you're 100 feet down and you have 100 foot of rod, you know, on that sampling bit. Like that 100 foot of rod is going to be really heavy. So that's going to change the amount of energy that is actually applied through that hammer, right? Compared to something super shallow. Some of these hammers are different sizes. So the size of the hammer is obviously going to be changing the number of hits, like the ease of it to penetrate through it. The type of hammer too. All of these things, there's this correction value that we have to put to that N value that normalizes it against all of these different variables. So the sampler, the SPT sampler, is, again, it's called the split barrel sampler or a split spoon sampler. And it's just a hollow tube that can be split in half and is able to collect soil samples from it. So the three main parts are the shoe. That's where it's actually like pushing into the ground. So this is like the tip almost. The split barrel section, and then the head that connects to the rods. And those two red parts highlighted can screw off of the split spoon sampler, and then it falls into two spots, and then we can collect data. So there's an important calibration process that we'll talk about here in a second. And so what they'll usually do is have one of these split spoon samplers and then instrument it using accelerometers and strain gauges, and that is used to actually measure the hammer energy applied to the soil itself. So you usually only do this like once every couple of years or so, but it's important because over time that mechanical hammer is going to lose its efficiency, and then it's going to change the amount of energy applied to the soil. So if we're all going based off of an energy output, we need to understand the energy input. So something like this is what like the samples would actually look like. Most of the time, like hopefully you get a full sample, so it's kind of hard to tell the color, but this is all filled with soil. You would then take a little section of it and put it in a jar and then send it to the lab. So the issue with SPT sampling though, typically SPTs are performed on a 5-foot interval. So every 5 feet we'll drill down and then take a sample. And the reason why we don't do it like every foot is because it would just take way too long, right? Like the videos showed kind of shallow SPTs, but normally you'd have to drill down, take the whole rod out, and then change the bit and then put it back in and then drill down and just go back and forth, back and forth. If you're 200 feet down, that's going to take like, a couple hours just to get like a couple feet or a couple samples. So we usually go every 5 feet. But especially in areas like, Florida, like 5 feet, we could easily skip a soil layer. So something like this here, like if we took a sample here, you can see this is like maybe this is like a silt. This is like a silt. But then right in between, we have this gravel layer that the sampler is actually missing completely. So we don't have a high resolution with depth if we're at every 5 feet. So FDOT tries to bypass this. FDOT for bridges or structures, other types of like large structures, they require every 2.5 feet. So that's at least a little bit more beneficial. You get a little bit better resolution with depth, but still you could easily miss a soil layer at 2.5 feet, or you could miss that that change between like a sand or a clay layer if you're just taking these point measurements every 2.5 feet in depth. But this takes a long time. So these bridge borings take a long time because of that drilling process of removing everything and going back and forth and going back and forth in between it. So most of the time now today, you'll see automatic hammers, but the hammer type, like if you look through like history, has been changed like drastically. Yeah.
Why do they take the sample out of the thing and put it in jars before it gets filled up? Like, why wouldn't they just bring you
Just transportation, it'd be difficult because you're usually like these drillers are in remote areas, so they'll just stack up these boxes, and then whenever the project is done, they will come and just drop off 20 boxes and stuff. So it's all just ease of transportation. Those jars too are watertight, so they're not like the bags that we used in lab. So they're meant like to take a quickly sample, get it out of the environment, and put it into like a moisture controlled area.
They're skipping every 5 feet and like warlock, they're just circulating soil.
Yep. Yeah, exactly. Yeah. So with the auger method, like that auger method where the soil comes up dry, that's beneficial because they can clearly see when the soil layers change. So in that case, like they could be like, okay, how deep are we? Like 61 feet. Okay, that's clearly going from like a red clay to like a blue sand or whatever. But in Florida, when we're using the wash method, you can't do that because what's coming up is driller's mud and it's all nasty like gray stuff. So you can't discern between when the soil layers actually change. We're going based strictly on the SPT sampler. So we're taking those point shots and we're just interpolating, or each engineer kind of has his own technique to determine what the soil layers actually are. So these are some of the hammer types that you'll see. There are different types. Automatic hammer is the one now that's like the most common. Literally the pin weight, donut, and safety, these are all manual types of hammers. So these require somebody with a pulley system, and they're literally just pulling this pulley and letting go of it. So it's like, there's two different types of pulleys. There's a cat head rope or the trip. And one of them is like an assisted pulley that is spinning. So it's actually connected to the motor and it's spinning. So you barely have to like pull it. But the other one, you're literally sitting there, like these dudes, like whatever delts are massive, probably just sitting there, pulling this pulley up and then letting go, pulling up the hammer and then dropping it. So the issue with these like manual versions are like Florida, 4:30 p.m. Like you think the driller is going all the way up to the top. Like he wants to get out of there. He's trying to like just finish up before he gets struck by lightning and the thunderstorm and stuff that's coming. So like these have to be corrected and they have to be taken with like a grain of salt. Like whenever you start looking at these reports, the first thing you should look for is the type of hammer used. If it's automatic, then you're like, okay, this is a machine that's doing it. It's out of the driller's control. Kind of, so like we should have a little bit more confidence. But some of these safety or donut or pin weight hammers, that is performed by like just the person's strength, and they can, they can take some shortcuts even if it's not intentional. So what these look like are here. The auto hammers again are like kind of the newer thing, and they're starting to use a lot more. But these donut hammers or pin weight hammers, they're literally just a pulley system with a rope. Most of the time, I think DOT now doesn't allow donut hammers and they don't allow pin weight, but they do allow safety still. So some old like drillers will use safety hammers, but the majority of the drillers are now going towards an automatic hammer because there's just less control in everything. And the issue that we see, like from this graph, this was actually performed at a study site of the same, like right next to each other. You can see how those blow counts, the end value, changes between different types of hammers. So like, this x-axis is showing the blow count values. You can see whichever one, this one, I think this was a safety hammer. The safety hammer shows larger blow counts. And that makes sense because if we think about it, the safety hammer is manual, and it is supposed to drop at a certain height. So the driller could easily just kind of like get tired and not pull it to the weight to the very top, and then it'll fall down with less energy. So if there's less energy penetrating the ground, then we should expect more hits to go the same distance. So that's why we have a larger end value. So what this is doing is telling us a false flag. We are thinking that the soil is stronger than it actually is just because the driller got tired after a long day of working and stuff. So to account for that, we use most of the time what is called an N60 value. So we take the N measured, which is just like counting the blow counts, and then we will correct it for 4 different things. So we will correct it for the hammer type, the depth, the borehole size, and the sampler type. So what some like sources use this Greek letter nu, others will use like a C. So you might see it as C, just the correction factor, something like that. But what we are putting in here is this N measured, and that's the raw SPT measurement. So that's the person counting it and writing it on the bore log. So that's in blows per foot. And then what we do is we correct it for 60% energy. So we're dividing it by 60. And then we have these variations of NH here, the borehole diameter. Depending on the borehole diameter, we use these values. Then the sampler type, we change the NS value. And then the variation of NR, that's the rod length. So that's one is really important, because if we only have a couple feet of rod and this hammer is hitting it, then the energy is going to refract up and down this rod. So we're actually losing energy because the metal is so short. That's why we correct it for rod length as well. So there's also other things that we'll correct this for. Sometimes you'll see this value as well. And we aren't quite there yet in the class. I don't want to introduce this, but we also correct. This corrects for overburden too. So this corrects a soil at 200 feet and compare it to a soil that is 5 feet in depth. So all that soil that is carrying this weight of the soil above it. So we correct it for the overburden, and we just put a 1 on the outside of it. They need to work on their notation a lot, but the N61 is the correct for overburden, but we'll cover that later because we haven't talked about overburden stresses yet, but you might see that when you start working too. So this hammer efficiency, this NH value here, you can see this is the one that kind of changes the most, right? Everything else is kind of in terms of like 1 or like variation of 1, but this one is the actual like hammer hitting and the energy applied to that. So this is a thing that we can actually measure. So there's been a lot of research, each manufacturer of these hammers, and there's a lot of them out there because it's like a public sector with a lot of like competing companies. But these NH values are manufacturer specific. So there's been research between each one to use the mean energy method and actually measure the type of hammer and how much energy is being applied to it. So that you'd find tables like this, and oftentimes like when you purchase drilling equipment or like the contractor, the driller contractor will already know the type of the energy ratio. So that will probably be provided to you. So you don't have to use this. But if they don't, then it's safe to assume some of the other ones like from the table a couple slides back. But these mean energy ratios, this is the same as that NH value there. So CMEs are a big one. This company, I don't know, this is the one that I've worked on the most, and they use this in Florida a lot. Some of the other countries might use some of the Dietrichs or any of the other ones. But so with this N value, we'll just kind of scrape the surface with it. But this N value is correlated to a lot of mechanical behavior indicators for the soil. So the strength of the soil, the permeability of the soil, the compressibility of the soil, all of these things that we use for design to quantify the mechanical behavior is corrected or found from that N value. So the N value is shown here. This is for sands. And you can see that N160, but this N value shows the different ranges. So for very loose, medium dense, and dense, and very dense. So with these N values, we can classify the consistency of the soil based off of what range it's in. So if we have an N value of 15 and it's a sand, then it would be a medium dense sand. And that corresponds to the relative density, which we've already talked about, right? And then these values here, this is called what's called a friction angle. And this is an indication of strength. So this tells us, even though we haven't covered it yet, but we'll kind of touch on it later on, but that friction angle tells us the strength of the soil. So if we can just do this one test, the SPT test, get an N value, correct it, then we can at least estimate and get an idea of the strength of this sandy soil using like charts like this shown by these guys, Terzaghi, Gibbholz, Skemno, Peck, all these dudes who have done this research and are still continuing to do research correlating the field test to the actual strength tests. If we're using clay, we see the same thing. So the N value is shown here, that N60 value. If it's less than 2, generally we call this very soft clay. And then we have these unconfined compressive strengths. This is again the strength version that we care for clays. But with clays, SPTs are not as accurate. So for sand and gravel and granule material, SPTs are a good test. But if you have primarily clay, then the SPT is not going to be the best bet, because thinking about like what is happening physically, like that is a hammer hitting this clay, this very soft, like sensitive clay. So if you took a hammer in the lab and started hitting clay, like it would just explode everywhere and you destroy the fabric, and you wouldn't get a good representation of the actual strength or the failing behavior for that. So keep that in mind when you start working. SPTs are still performed in clays, but you have to take those numbers with a bunch of asterisks because it's not designed for that fine grain material. Oh, we'll get to that in a second. So this is an example. I already have this stuff shown on there, but you can go through that to kind of help you with one of your homework problems. But again, if we have the report like this, what you would see, even though it might be hard to read from the screen, there's 3 numbers. There's 8, 13, and 16. And this is at a depth of 51 feet. At 51 feet. So the N value that we would take from this is the addition of the last 2. So 13 and 16. So most of the time you'll actually see that initial N value is lower than the last 2. And that's because that first N value is pushing through the mud and the cuttings at the bottom of the drill hole that settle down. So we want to be pushing through like natural material. So that's why we only take those last 2. So like for at 53 feet down here. So where is that? 53 right here. So this is the sample taken from 53.5 feet. So the last 2 would be 24. So our N measured is 24, which is 12 plus 12. And then we would need to correct it for all of these things here. So if we said that it's an 82% efficiency auto hammer at 53 feet, our NR is 1, our sampler is just a standard sampler, so it's 1, and our NB is the boring size. You check that table again and make sure that it's the same. And those are all 1s. So the correction is relatively easy here. We'd say like, even though we were measuring a below count of 24, the actual like N60 value that we would plug in and like provide for the client and use everything in the correlation would be 32.8.
On the sidebars where it starts with the 8 in the red, why did you not include the 2s that are below the 3 1?
Oh, right here. These, yeah, I just didn't. I skipped that one because I didn't want to jumble it too much. Yeah, so this 1, 2, 2 is missing from the little line up here. Yeah, normally you would though. So like this is a common thing like entry-level engineers would do. They take these reports and then they would actually write down, calculate the N value associated with each like soil layer here. And then they would make remarks and observations like based off of the soil here. So that's where you'd see the classification. So right here, like I was saying, this is an SPSM, this is an MLMH, And then we would do the further lab testing to actually classify it either an ML or an MH and so on and so forth. So there's a homework problem that you need, obviously need to know this for and everything. So we work with soil a lot, but in other areas, and I mean, even in Florida, what we also care about is rock samples. So the rock samples are important for mineralization. So understanding the actual geological depositions and knowing what type of, geologic conditions are there. We can also take rock samples and perform direct shear testing, so direct testing on it. Rock samples are really important in areas where the rock is super shallow. So in areas of Florida, like Tampa, where you just go like 10 feet down and there's rock. Gainesville and up closer in the panhandle where the bedrock is shallower, you'll do a lot more of these rock sampling. And this is also super, super big for petroleum. So this industry has a lot more money, obviously, because natural gas and oil is within these rock strata. So the drill bit, or if we were to use the hammering process, same for soil, like pushing and hammering this drill bit into the earth, then that would not be able to collect intact rock samples, right? We'd just be destroying the rock. We'd get a bunch of little pebbles up, but we would want something like this, a coring process. So the rock coring process, I have a really short video, is really interesting because it uses a double barrel. So we need to spin and push into the rock, but we don't want to spin and shear the rock. So it's actually like
drilling process includes
the inside.
three
Yeah,
major
I'll explain it, whatever.
the actual drilling, the retrieving of the core sample, and resuming of the drilling. Together, this is called a round trip. And for each round trip, the drill hole is extended by the length of 1 or 2 drill rods. There are 2 core drilling methods, conventional and wireline. The main difference lies in the method used for bringing up the core samples to the surface once the inner tube is full. In conventional core drilling, the entire drill string has to be pulled out of the drill hole in each round trip. In a 150-meter deep drill hole, this could mean that the drill rod threads need to be broken and joined back again up to 50 times for each core sample. In wireline imaging, a so-called overshot is sent down to release the inner tube. The overshot and inner tube are then hoisted up to the surface with a wire. A new inner tube is lowered down and locked in place. This method is much more productive, efficient, and safe. During the drilling process, a drilling fluid is flushed down the drill string to cool the drill bit and to transport the cuttings to the surface. When the drill bit is worn out, the whole drill string has to be taken out of the drill hole, regardless of drilling method. Therefore, choosing the right drill bit for the formation is extremely important for high productivity. Between each round trip, the driller stores the core samples in core boxes. The driller logs the time and date of the drilling, as well as depth, core recovery, and possible losses. These high-quality core samples are the final goal of the core drilling process.
So with this technique, we obviously aren't getting like an N value or a below count. We get physical samples. And there's a value that still tells us, gives us a representation of how strong that rock is just from the test itself. Do you have a question? Yeah, that directional drilling that guy's for petroleum. That's really common in petroleum because then you can get a wider footprint too. So these layers are horizontal. So like if you go sideways, then you can, get any seams at a different direction or something like that. So they get a little bit more understanding of it. For geotech, most of the time, we're not going 1,000, 2,000 feet deep like the petroleum people are. So we just go vertical. So we have 2 values, rock quality index and the recovery value. So the rock quality designation is a very simple calculation. Actually, both of them are. And this is something that gives the engineer who's looking at the samples a relative like idea of the strength of the rock before doing any actual tests. So they may still take a sample. They may still take, you know, like a sample of this and bring it to the lab and actually break it. You know, these are like little cylinders, so they could actually put it in a compression test and do an actual test on it. But they'll also calculate these values. So the recovery is very basic. It is the length recovered divided by the total core run length. So if your drill, if the actual like core run was, you know, supposed to be 10 feet and you only got 8 feet of material from that 10 feet like of length, then, you know, 8 divided by 10, you'd have a 0.8 recovery or 80% recovery. And then the RDQ is very similar, but instead of looking at the total sample, you only count the length of sound core pieces. So these sound core pieces are pieces of rock that are greater than 4 inches in length. So if you bring up a bunch of like little tiny like samples like this right here, where it's crushed rock, this would not be included in that length because all of these are like less than 4 inches. But then it's still, you divide it by the total core length run, and then it's all in a percentage from 0 to 100%. And we have these descriptions of the rock quality. So if you have an excellent rock, then that means you have 90 to 100% of this RDQ or RQD, rock quality. Yeah, my bad. This should be opposite. So in Florida, we pretty much will never really have excellent to good unless you're really deep, because that limestone bedrock that we have crumbles a lot during this process. And it's just not, you know, it's not like a solid chunk like you would get for granite or something. Up north, like Panhandle of Florida and closer to Georgia, you get a higher rock quality designation. But most of the time in South Florida, the peninsula, you'll get some low quality rock. But that's good because that gives us our aquifer and all that fun stuff. So it's a give take. So this example is actually taken, this was on my PE. So they ask you this on the PE. So I'm sure they'll ask you it on the FE too. This is they say a rock core is advanced from 20 to 25 feet, which of the following is true. And they give you this like little cutting diagram here, right? So remember the RDQ. Geez, that should be RQD, whatever. You guys get the idea. This is only, we count all the pieces that are greater than 4 inches. The recovery is just all of it in total. So if we know the total here could have been 5 feet potentially, then our recovered, just add up every single chunk. So 12 inches, 1 inch, 16 inch, 2/3 inch, whatever, all of these like thicknesses here. And then of course we need to put that into feet to divide it by 5 feet. So we get 4.25. So that means our recovery down here is 4.25 feet. We got 4.25 feet total of sample that we divide that by 5, 85%. So we know this is not true. Recovery is not 80%. Our RQD, we count everything that is greater than 4 inches. So we don't count the 1 inch, don't count these, don't count this. So we only have 12, 16, 12, and 8. That's 48 inches, 4 feet. So 4 divided by 5, that's 80. So we know that this is our true value. So you'll see like a lot of these tests are quick. Like you just get a sample, like you get the box of cores, and you might do additional testing on it later, but you can quickly at least find this quality designation based off of what the driller gives you. But you know, some of these could be sheared naturally, or some of these could be an actual break in the rock, you know, underground due to the equipment, the drilling process. One of the funnest things when I was on a drill site, they were doing this next to us, and the head driller and like the assistant driller literally got in an argument over the best drill head to use, the drill bit to use for like an hour and a half, and they were just like speaking a different language in my mind, because they're like, a diamond cutter 3000, and just like legit arguing over the type of drill bit. And I was just like, yeah, I wish I could contribute. So yeah, it's, I mean, there's a lot of variables in there, because it's up to the driller to use the type, this consistency of drill mud that it's going to cool off the drill bit at a significant temperature. And they also, you need to know when to change the drill head and all this stuff like that us engineers don't know is happening behind the scenes. Okay, so sand, SBTs, rocks, obviously we use cores. For clays, we have a special test that is much more sensitive, but it's newer. So this is the cone penetration test. This was really like, if you remember, SBT was like around in like 1902. And the most modern versions of the cone penetration test that are electric, these didn't come around until like 1980s. So this is a relatively new type of test, but now it's becoming more and more popular. It follows ASTM 5778. And the main benefit of this test is we get data. So we get data every like 2 centimeters. So before with the SBT, we were collecting data at 2.5 feet with depth of like average. So now we can collect data every like 1 inch now, basically with depth. So it's much more higher resolution with depth. But there's still some limitations with this. But what we're generally measuring, and here what the general details of looks like, it is a truck that hydraulically pushes these probes, and these probes can have different sizes. So this cone tip is the one that pushes through the soil, and we measure 2 things. So we measure the cone tip resistance. So that's the actual resistance on the tip itself from the soil pushing through. And we show this as a QC. And this is in terms of like a stress. So this is obviously shown in tons, or usually shown in tons per square foot, or like megapascals. So this is a stress. And we're also measuring the sleeve friction. So the frictional resistance along the sleeve behind the cone tip. So you can see there's almost 2 parts there. So the sleeve friction is also measured in tons per square foot or megapascals, something like that. And what we get with this is real-time results, which is super nice. And since it's all electronic, it's much more, I don't want to say accurate, but there's less variables as long as we have the electronic system calibrated correctly. So the cone penetration test is also rate controlled. So it's not a hammer pushing into this. We're pushing it at a constant 2 centimeters per second in depth. So if you're a clay hanging out down there, you're not getting hit with a hammer. You're just getting like a butter knife pushed through it and measuring it. So it's much more sensitive to like fine grained material. And a value that's really helpful that we calculate is what's called the friction ratio. So that friction ratio is shown in usually percentage or just a decimal form, but it's the friction, or this friction divided by the tip resistance. And again, this is really helpful because it shows real-time results on like the computer screen there. The engineer is sitting, or the driller is sitting in this air conditioning. They're not worried about trying to get home super quick. They're not like getting bit up. There's less, distractions. They can better like control the rate or understand that like which soil layer needs maybe more investigation. So if we look at the results compared to each other, then we see very similar trends. But what I want to highlight is this area here from our SBT, where our N value is 0. So this is actually pushing through a very low plasticity silt. And this silt is so weak or so soft that the N value doesn't have any resistance. The rod actually just falls through it. And this is from a depth of like, 27 to like 45 meters. So pretty deep. If we use the cone penetration test, like we see here, we're still getting some values. So you can see we're still collecting some strength values where the SBT is showing that it's just a complete like loose material or like a void. So the cone penetration test is really popular in areas where you're expecting this loose material or like a very like soft clay. And you can also see just by looking at like the graph, like we're interpolating the strength values at, in this case was like every couple meters. But with this the CPT, we get a lot of data with depth, and we can clearly discern between soil layers. Like this, for example, like we can see here, this soil layer is obviously a specific soil layer where for this one, it gradually increases and decreases. So it's much more sensitive. Cone penetration testing also can happen much quicker. So a standard penetration test, usually to get like a 60-foot boring out of it, it'll in Florida generally be about like half a day to do like just one boring. For a cone penetration test, you're literally just poking the hole down and pulling it back up, and then that's it. So you can do like those tests very, very quickly. The issue with cone penetration tests, though, we don't get a sample. So this is the one like kind of pitfall with this test. We don't get a physical sample. So we get a lot of data. We get friction ratio. We get all of these like different data. We can get pore water pressure with it. We can equip this probe with a bunch of other like tools, but we don't get a physical soil sample to do other tests on. So that's the limitation with this. So it's a give and take. But there is a lot of research performed that by this dude Robertson, Godfather CPT, where we can plot and understand the soil behavior correlation. So this isn't soil type, but it's a technique used to estimate the most probable anticipated soil that we're pushing through. We can't say for sure because we don't have a physical sample, but charts like this help us at least guesstimate the type of soil that we're pushing through. So you see that it's a scattered chart, base chart, where we have cone resistance on the y-axis and then friction ratio on the x-axis. And what the data would look like if we plotted this, it would group into a certain area. So we'd see all this data up in here. And that means if it was all in the 6, that would be a sand, clean sand to silty sand, something like that. Likewise, like if we had a very high friction ratio and low tip resistance, all that data would be down here in zone 2. And we would see, okay, this is most likely an organic soil or a clay. So this is only behavior though. We can't like actually define the sample. But since this is all electronic, the benefit is now we can actually plot this real time. So there's software that will perform the CPT and take that data as it's being collected. And then I actually shoot out these really pretty soil profiles with depth. And this is again, while you're actually doing the test. So what we're looking at here is actually the ground surface elevation. So the ground is up here, and then we have depth shown here. And you can see they even color code it, which is always pretty. And we can see that what type of soil we're most likely penetrating through with depth, as well as the cone tip resistance and the friction ratio too. So although CPTs don't actually allow us to collect soil samples, they still give a lot of information and at a much higher resolution with depth compared to the SPT. So the cone penetration test, it's highly adaptable, which is super beneficial. So we can actually use it to measure groundwater table a lot easier. We can measure permeability directly. So there's actually some tests where the cone has a hose running through it and it allows water to seep out of the cone as it's being pushed, so it can measure the rate at which water is flowing underground. It can also be used in seismic applications, which is super nice. So we can put like geophones or accelerometers on it, and then at the ground surface, hit the ground with a hammer, and we can measure the energy wave going through the ground, and we can estimate like its resistance to liquefaction or something that way. It's quicker, which is super nice compared to the SPT. And it's much more sensitive. So for clays, we'll see SPTs, the N value will generally go to like close to 0. But then for CPT for clays, we could have a value still about 10 TSF. So we can at least get some strength value and still estimate the tip resistance for that. Cone penetration tests are really popular for geohazards. So especially sinkholes, we're starting to use that a lot more because it's a quick test, you know, and also it's less intrusive. If you have a potentially forming sinkhole, you aren't hitting it with a hammer. You don't want to be like using a super like intrusive test and washing all this liquid. So we use a CPT, a nice quick and you know, less intrusive sinkholes, and then also for liquefaction. So for earthquakes and for landslides. So due to its accuracy, we can actually pinpoint the exact like location in a subsurface profile where a landslide may potentially form, like a slip plane or something like that. It is dependent on the weight of the ram / the vehicle. So you can only push as deep as how heavy the equipment is, you know, like for me, like if a guy is just doing a hand CPT, like you can't push it that far because you're eventually going to be lifting yourself up. So same thing when it comes to like the truck, you know, like most of these larger trucks are super heavy, and you can at least push down, you know, into the bedrock, but sometimes it's a limitation because you're pushing and the truck is lifting up. It's also super dependent on the money, like so the startup cost is a lot. You know, since it's all electric, it's all like new state of the art. To fix it is a little bit more money too, just because it's not as standardized right now. And of course, the biggest issue is no samples. So most projects you will see use both SPT and CPT, especially some of these roadway projects in Florida. They'll use SPTs to actually classify and get hands on a soil sample and do lab tests. But then if they encounter any like really thick layers of clay, then they'll bring the CPT truck over and then do a few point measurements too to get a better understanding of the clay layer. So these are two tests, CPT and SPT you'll come across. You might also come across the rock quality designation, especially on the FE, because they like to ask that question for some reason. Okay, so that's it. Next week, we will get over soil compaction. There is going to be a quiz this week. So it's going to be a short quiz. I have the lab and then I'll post it by like 2 p.m. today. So keep an eye out for that. It's not going to be posted right away. I need to finish some stuff up on it. All right, guys, enjoy your Thursday.